Hi everyone, my name is James Larish, and today I'll be talking about a new system at Cloudflare called Topaz. So I worked on this project while an intern at Cloudflare during my PhD with these collaborators, but I've since graduated and now work full-time on the Cloudflare research team. In this talk, I will describe Topaz, a rules engine for authoritative DNS behavior at large networks like CDNs. Using Topaz, operators express DNS rules declaratively using a custom domain-specific language. They can change these rules globally within 10 seconds, and all changes are checked by our formal verifier. Topaz is a research system that's currently in production and processes 1 million DNS queries per second at Cloudflare globally. I'll proceed as follows. First, I'll provide some background on how Cloudflare uses authoritative DNS and problems with Cloudflare's old system for managing name server behavior. I'll then describe the new system Topaz, including its architecture, domain-specific language, and formal verifier, and then I'll conclude with evaluation and lessons learned. To understand what Topaz does, I first need to explain what CDNs like Cloudflare use authoritative DNS for. Say you have a website, example.com. You sign up for Cloudflare, so you make their DNS name server authoritative for example.com. Clients query Cloudflare's name server for your domain and get back a Cloudflare IP address, advertised by a Cloudflare server, which the client connects to. Cloudflare applies caching and security rules and maybe forwards the connection to your origin server before responding to the client. Importantly, Cloudflare is a global Anycast CDN, which means all of its data centers advertise all of its IP addresses via BGP. To illustrate how Anycast changes things, imagine Cloudflare only operated in Australia and owned one /24 prefix shown here. Due to Anycast, all three data centers advertise this prefix. So when a client in Sydney queries example.com, gets an IP and connects to it, BGP routes this connection to the logically closest Cloudflare data center. The upshot is that Cloudflare does not perform DNS-driven routing or load balancing like many unicast CDNs. It relies on BGP to get client packets to a Cloudflare server. Despite this, Cloudflare's name server still has an interesting decision to make when it receives queries, namely which IP should I return. Simple name servers map names to IPs, but CDNs break this model. In fact, previous work done by my colleagues, called the ties that unbind, proved that CDNs can completely decouple names from CDN IPs. In practice, networks like Cloudflare return specific IPs to satisfy internal and external service level agreements, which we call addressing objectives. Here are three examples of addressing objectives. The first says that all DNS queries received for Tier 1 customer domains should receive some IP from the Tier 1 prefix. The second says the same, except for Tier 2. And the third says that 10% of all queries received in Sydney should receive the IPX. These resemble objectives deployed to Cloudflare today, so I'm going to use them as examples going forward. But let me explain them a little. The first two are used to assign different classes of traffic to different prefixes, often for the benefit of downstream systems that operate on the level of IP prefixes, such as our Layer 3 load balancer. The third objective is used for A/B testing. So if Cloudflare deploys a new feature or new server and binds it to a particular IP, in this case X, it can use objectives like this to forward a small percentage of traffic to that service and then ramp it up if this experiment is successful. To get name servers to satisfy these objectives, Cloudflare employs a centralized periodic cron job called an assignment or mapping system. This system takes as input a set of DNS metadata, such as all the domains the CDN is responsible for, and the set of IP prefixes owned by the CDN. It periodically matches DNS metadata with IP address while trying to satisfy the operator objectives, emitting a set of assignments from DNS metadata like domain name to IP address. These assignments are distributed to the CDN's edge network name servers. Each name server maintains a copy of these assignments, and when one receives a DNS query, it looks up the corresponding IP address in the set of assignments and then returns it to the client. Note that other CDNs like Akamai have similar systems, though their objectives differ. Unfortunately, Cloudflare's assignment system suffers from two main problems. The first is that policy decisions are made imperatively by the assignment system long before those decisions are actually enforced at name servers. The resulting assignments don't tell operators why certain queries received certain IPs. Similarly, it's hard to know whether a new or modified policy has actually taken effect just by looking at the assignments. Which leads to the bigger issue. The effects of two objectives often interfere with one another. In fact, two of our objectives can conflict. Tier 1 queries made in Sydney can trigger both the Tier 1 and the 10% in Sydney objectives. Picking either policy leads to a bug. Unfortunately, Cloudflare's assignment system swallows these types of objective conflicts, which has caused incidents. To fix these problems, we built Topaz. The primary insight of Topaz is thus: rather than imperatively generating assignments with no context from objectives, let's just execute the objectives directly as programs. We call these programs policies. These Topaz policies are compiled into a list and distributed to every name server on the edge. All name servers store a copy of these programs, policy programs, and execute them in response to every single DNS query they receive. This approach has the following benefits. First, to understand a name server's behavior, operators can simply read or execute the list of policies directly. Second, to change behavior, operators simply add a new policy program or change an existing one. Finally, by carefully designing the policy language, we can formally verify the safety of these policy programs. I'll now explain how Topaz works. Here's the pipeline of Topaz policies from construction to execution. This pipeline runs whenever a policy is added, removed, or changed. Let's start with construction. So the challenge here was providing a generic way for operators to express powerful policies that can be easily changed, but still formally verified. We did this by decomposing the policy structure into two main parts: the circumstances in which it runs and how it chooses IP addresses. To illustrate this, consider a contrived policy that maps all queries for example.com to IPX. Its desired circumstances are all queries for example.com, and it chooses IPs very simply. It always returns the same IP. Operators express these two components separately, so the circumstances in which the policy runs here is expressed using what's called a match function. This policy's match function is an equality expression that checks whether the query name is equal to example.com. On the other hand, the IP choice procedure is expressed using what we call a response function. It is an expression that evaluates to an IPv4 address shown here. However, these are simplifications. In practice, the signatures for the expressions look more like this. The match function, as we've seen, returns a Boolean, it's the same, but the response function actually returns a 3-tuple, which includes a list of IPv4 addresses, list of IPv6 addresses, and the TTL. So in reality, the response function would look more like this. Now, there's a third component to policies called the policy's configuration. You can think of configuration as a set of global variables that parameterize the match and response function. For instance, we could parameterize the domain, example.com, by referencing a value in the configuration. Similarly, we could abstract the IPs and the TTL in the response function by referencing values in the config. Quick note, this policy was purely for exposition. We actively discourage name-based Topaz policies because they do not scale and are counter to the idea of policy-driven rather than name-driven name server behavior. Here's the same decomposition but for the Tier 1 policy. The match function checks whether the query's service tier matches the configured value, in this case 1, pretty simple. The response function, though, is more complicated. It hashes the domain name in the query and then selects addresses from the configured IPv4 and IPv6 prefixes. The select function returns the same set of IP addresses from a given prefix when given the same hash. This logic ensures requests for the same name get the same IPs while giving different query domains different IPs. Quick aside, let me just describe the policy language that we built, Topaz Lang. So it's a Lisp-based DSL. Every expression evaluates to one value, but there are runtime errors. It's dynamically typed, and the language itself is not turn complete. Users cannot define new functions in the DSL, but they can define new built-in functions in the host language Go. It has familiar types like primitives and collections, but also types relevant to DNS like IP prefixes and TTLs, which help prevent certain bugs. If interested in the precise semantics, please see the paper. So back to policies. The three components of a policy are stored in a YAML file that looks like this. In fact, all policies executed by Topaz are expressed in a single YAML file. Critically, when an edge name server receives a query, it executes policies in this order until a match function is returned. A match function returns true. It then calls the response function of that policy and returns the results to the client. This policy file is stored in version control, and when a policy change is merged, the policies are validated, which includes some basic static analysis. and after that, policies are augmented. Augmentation transforms policy configuration into a final form. So for instance, consider the following configuration that has a value called EU data centers, populated by a built-in function that fetches all of the Cloudflare data centers in Europe from an API. During augmentation, functions with dynamic sources like this are executed, and the result, the EU data centers, are stored in the config and sent to the edge. The final policy list is then formally verified. At this stage, each policy's match function and configuration are passed into our model checker, which was written in Racket and Rosette, to check for bugs. In short, our model checker generates symbolic requests and checks for these properties. The first property verified, satisfiability, ensures that there exists a request that causes each match function to evaluate to true. If not, it throws an error saying there is no request that will satisfy the policy. Here we can see the match expressions for our 3 example policies. Check out the Sydney 10 policy, which checks that the location is Sydney and that a random number between 1 and 10 is equal to 1. So for instance, if we changed the service tier 2 policy and made its match function contradictory, our verifier would throw an error because the match function is not satisfiable. Reachability is an extended version of satisfiability. It checks whether there exists a request that satisfies each policy given all preceding policies. Since, recall, this order specifies the order of execution. So if we made the service tier 1 match function the true expression, this would render the subsequent policies unreachable. The final property is the one engineers at Cloudflare are most excited about. It checks whether two policies conflict, that is, whether there exists a request that causes both policies to match. It only checks this for policies explicitly marked as exclusive. So let's say all were marked exclusive, as shown here. The verifier here would throw an error because there exists a request that could match both the service tier 1 with service tier 1 value and Sydney 10 with location Sydney. Operators must resolve conflicts like this manually. So in this case, they could mark the third policy as non-exclusive and then accept that the preceding policies would have higher priority. Once done, the verifier will no longer throw an error. Verification raised a number of challenges. Rosette and its underlying SMT solver can only operate over certain unbounded domains, so we use enums for strings where possible and bound the size of certain types such as lists and sets. We also needed to model random values, so we model random integers, for instance, as symbolic values bound by the random range. This required adding special logic in the verifier for any function that uses randomness. Finally, policies, once verified, are pushed to Cloudflare's edge using our global edge key value store. This takes about 10 seconds to propagate. Every name server thus receives a copy of the same sequence of policies, such that when a client queries the name server forwards the request over IPC to the Topaz service running on that server. The name server and Topaz are actually 2 distinct services running on every server in Cloudflare's network. We chose this architecture because it allowed the research team to iterate on the internals of Topaz while keeping its interface static. So Topaz runs the query through the sequence of policies until a policy's match function returns true. It then executes that policy's response function and forwards the result to the name server, which returns the resulting IPs to the client in valid DNS format. So Topaz today is deployed and running. It's actually possible that you've made a DNS request today that ran a Topaz policy. There are 7 policies live, 3 of which are marked exclusive, and 2 of them are similar to the service tier policies I showed, and 2 are similar to the 10% policy. It receives 1 million queries per second globally, and 100K of those per second result in a policy match. When no match is found, Cloudflare's name server falls back to the legacy logic, which we're currently phasing out. Topaz aims to provide qualitative benefits, but it has quantitative costs. If we consider all DNS requests made to Cloudflare, Topaz's latency in the 99th percentile is 0.07% of the total DNS request latency in the 99th percentile at Cloudflare. This is acceptable for us, but we are exploring folding Topaz into the name server to eliminate IPC cost. Verifying the live policies takes about 6 seconds in the current CI pipeline, but for more info on verifier performance, please look at the paper. Generally, Topaz has been a success within Cloudflare, but it's not perfect. The major strengths are as follows. First, the match action paradigm is really nice because it's easy for operators to understand the most important part of a policy when it runs, the match function, at a glance. It allows match functions to stay simple and be easily formally verified, while the response functions can be arbitrarily complex. Second, centrally compiled but globally executed policies has also been really nice because every name server behaves in the same way and name servers can be easily debugged. On the other hand, Topaz has weaknesses. First, the separate model checker must be kept in line with the Go Topaz Lang interpreter. Normal engineers have trouble with the racket and verifier code. Second, choosing a Lisp-like language for the DSL made building the interpreter easy, but we suspect it puts some engineers off. So if given the choice to go back, we'd probably have made the syntax closer to something like Python. That being said, some engineers really like it. So I'll wrap up with some quick takeaways. Topaz demonstrates that translating business requirements into code that is executed directly can help manage complex, conflicting SLAs. But Topaz's real win is applying formal verification to policy code that changes frequently. Engineers are most excited about this since it helps prevent incidents. Also, the success of the match response paradigm in Topaz reinforces its prevalence across the literature. In the future, we hope to move all of Cloudflare's addressing logic into Topaz and explore optimizations in Topaz Lang and Topaz. We've also experimented with using Topaz for other records like HTTPS and hope to continue to do so. For more info on that, please see the paper. Thank you.